Good afternoon. This is your 7 digital class for the subject physics. Now, in last class we discussed about electric field intensity, and dipole. Now, today we are going to discuss electric dipole in uniform electric field. Now, in last class we discussed that uniform electric field, basically in uniform electric field, the magnitude of the field intensity and direction remain same throughout the field. Now, today's topic, electric dipole in uniform electric field. So uniform electric field basically defined by parallel lines with a constant gap. These are the field lines. Now the arrow is towards this side, so this is your field E vector. Now in this field, what we have done, we have placed a dipole. AB is your dipole. It has two charge, one is your minus q and another one is your plus q. So what happened, as per the definition of the field intensity, there is a force on the charge plus q, and this force directs along the direction of the electric field, that is your q E vector. So definitely there is a force on the charge minus q, and the direction is opposite to the direction of the electric field because due to the negative charge. Now if we define the total force exerts on the dipole, then the total force comes out to be your F vector equal to q E vector plus minus q E vector equal to 0. So you can say the system is in translational equilibrium because net force is 0. Now let me try to define torque, and torque is nothing but is your rotational parameter. So if torque comes to 0, then rotational equilibrium will be there, but let's see what is the value of the torque. Now as per our previous class in the sense that the topic which we discussed in class 11, torque. Now torque is nothing but is your moment of force. Now mathematically torque can be defined by this expression. Magnitude of either force, you do have two forces are here, one is your q E vector, another one is your minus q E vector. So you can consider magnitude of these either two forces and the perpendicular distance between two forces. So this force direction is towards this side and this force direction is towards this side. If you have to draw a perpendicular to the line of action of the force, then BC is your perpendicular to the line of action of the force. Now as per the definition, torque is equal to magnitude of either force, perpendicular distance between the two forces. So magnitude of either force, it comes is your QE and perpendicular distance is your BC. Now if you go for this triangle ACB, then BC comes out to be your 2L sin theta, and 2L is nothing but the length of the dipole. So QE 2L sin theta. So if you simplify this one, Q2L E sin theta. So Q2L is nothing but is your dipole moment as we discussed in our last class. So now torque equal to, that is tau equal to, torque is basically denoted by tau equal to PE sin theta. So in vector form you can express tau vector equal to P vector cross E vector as per the definition of the cross product. Now you can go for two condition under the condition for the values of theta. If theta equal to 0 degree, theta equal to 0 degree means this dipole is along the direction of the field. So under that case torque comes to 0 because sin theta is your 0. Sin 0 is 0, that's why torque goes to 0. If theta equal to pi by 2, theta equal to pi by 2 means the dipole is perpendicular to the direction of the electric field. So ultimately we will get tau equal to PE. So this is very important topic and frequently it is used to come to exam. So go through this topic very thoroughly. Okay, and maximum marks it carries 2 marks. Now let me go for another topic, that is your area vector. Area basically is a vector quantity and the direction of the area can be defined by the normal drawn to the area. Normal is nothing but the perpendicular and magnitude is nothing but the numerical value of the area. So area vector, a small element of area of a surface enclosing a given volume can be represented as a vector. Now this is your large area which we denoted as S, and out of that we have considered a small elemental area, that is your ds. Now if we have to define the direction of this ds, then what we have to do, we have to draw a normal. So ds vector, so n cap ds. N cap is nothing but the unit vector and ds is your magnitude. So if someone asks you find the direction of the area, what you will do? You will draw a normal to the area, and the direction of the normal gives you the direction of the area. So this is very important part for our coming topic, that is your area vector. Now next let me go for the electric flux. Now electric flux, when comes to the term flux, flux means a large number of field lines. Field lines already we have discussed. So if you collect field lines, then that together can be defined as your flux. Now basically let me go for the definition. It says that electric flux linked with any surface can be defined as the total number of electric field lines passing through that surface. Let me repeat once again. Electric flux linked with any surface can be defined as the total number of electric field lines passing through that surface. So as per the definition, does it seem that it is only a number? The definition says electric flux is just a number, but practically electric flux is your physical quantity. The definition defined that it is proportional to the number. Proportional to the number means if the more the number of field lines is there, then more flux will be there. Okay, otherwise electric flux is your physical quantity. It has its specific unit. Now numerically, mathematically, you can define flux d phi equal to E vector dot ds vector. This is your mathematical expression for the flux, and flux is denoted by phi. If the flux is small quantity, then you can define d phi. So mathematically it is E vector dot ds vector. So if you go for the dot product, it comes to be your E ds cos theta. Now under this condition, theta equal to 0 degree, you will get d phi equal to E ds. If theta equal to pi by 2, then d phi equal to 0. So if we consider this area, the direction of the area is perpendicular to the plane, and field is also directs along the same direction. It means what? E and S, they are in same direction. If E and S in same direction, then it means theta equal to 0 degree. And under that case, you do have a flux d phi equal to E ds. This is the maximum value of flux. Okay. Now if we consider this one, suppose field lines passing through this surface S, over the surface basically, then normal is your S vector. So S and E is perpendicular. So if S and E is perpendicular, then you will get d phi equal to 0. It means there is no flux. Now flux is your physical quantity, so definitely it has some units. So if we go for this one, E ds, E is your field intensity and the unit for intensity is your Newton per coulomb, and ds is your area, so it's your Newton per coulomb meter square. Now dimension, regarding dimension, again you go for this one, E ds. E ds is your force per unit charge. Force is your m1 l1 t minus 2, and charge is your at, and area is your l2. So if you simplify this one, it comes out to be your m1 l3 a minus 1 t minus 3. So this is all about your flux, and flux is proportional to the number of field lines. If more number of field lines passing through a surface, then the flux will be high. Now let me go for this topic, Gauss's theorem, and this relates with the flux. Now what it says that the total electric flux through any closed surface in free space is equal to 1 by epsilon times the total electric charge enclosed by the surface. So epsilon already we have defined in our first class, that is your absolute permittivity. Now this theorem let me try to prove, and this theorem says total flux is nothing but is your Q by epsilon naught. Now Q is your total charge enclosed by the surface, and epsilon is your permittivity. Let me repeat the statement once again. Please go through. The total electric flux through any closed surface in free space is equal to 1 by epsilon times the total electric charge enclosed by the surface. So let me go for this diagram. This is your spherical surface, and at the center you do have a charge plus Q. So what will happen? The field lines will be out of this charge, as it is positive. Already we have defined why it is outward. Now let me consider a small element over the surface, spherical surface, that is your ds. Now E vector is radially outward, and similarly if we consider ds, then the direction is also radially outward. So E ds both have the same direction. So if we try to define the flux, that is your d phi, then it is your, as per the definition, it is your E vector dot ds vector. So E ds, as both are same direction, that's why E ds cos 0 degree, that's your E ds. Now if we interest to define the total flux, this is your small amount of flux that passes through this small surface ds. Now if we try to define the total flux through this closed surface, so what we'll do, we'll go for the closed integral. This is your integration sign, and this small round define the closed integral. So what we will do, E is a constant at every point over the surface because distance is fixed, and E is your kq by r square. So if r is same throughout the surface, then E is constant, so E comes out from the integral sign and you do have ds. Now ds is your surface, total surface, that is your 4 pi r square, and E is your 1 by 4 pi epsilon naught q by r square. So ultimately we will get on simplification q by epsilon naught. So which is the expression for Gauss's theorem. Now what this Gauss's theorem says that the total flux is independent of the nature of the surface. Because you see the parameter phi equal to q by epsilon naught, there is no parameter related with the nature of the surface, whether the surface is spherical or cylindrical, it is not specified. So it is valid for all surfaces irrespective of its nature. So total flux is nothing but q by epsilon naught. So this is very important point. Number 2 point, if the enclosed surface does not contain any charge, then total flux goes to 0. So let me try to implement this formula in a numerical. This numerical, a point charge of 1 microcoulomb is at the center of a cubic Gaussian surface having side at 8.55 centimeter. What is the net electric flux to this surface of the cube? So Q equal to 1 microcoulomb is given, so 1 into 10 to the minus 6 coulomb, and from Gauss's law phi equal to q by epsilon naught. So if we substitute this value 1 into 10 to the minus 6 and the value for epsilon naught 8.85 into 10 to the minus 12, then you will get 1.13 into 10 to the 5 Newton meter square per coulomb. So this is very simple, as only you have to substitute the value. So this is all about your 7th number of digital class for the subject physics. Now go through this topic. This topic is very important because it's quite uncertain whether or when the offline class will be there. So it's very important, this online class. This is basically digital class. So be concentrated on this topic and try to find out doubts, and if you have any query, you are free to ask. Thank you.